Hello everybody and welcome to our video on antiderivatives. So an antiderivative is exactly what you think it would be, or at least should be. It's just the reversal of the process of taking a derivative. So we define a function f is called an antiderivative of f, little f. So we use capital F for the antiderivative and lowercase for the original function. So a function, cap f, is called an antiderivative of f on an interval I if cap f prime of x equals little f of x for all x and I. Now, one of the things I'll just point out here, an antiderivative is a key word because, well, they're not necessarily unique. So let's see that, for example. So find an antiderivative of f of x equals x to the fourth. So when we're looking for antiderivatives, we just have to kind of think backwards a little bit. So this is a power function, and I know that if I take the derivative of a power function, I get another power function. So what could cap f of x be? Well, how would I get x to the fourth? Well, the power would have had to have been the fifth before, so it should be like x to the fifth. But if I took the derivative of x to the fifth, I should have a 5 out in front, which I don't have here. So to cancel that, I must have a 5 on bottom. So if you're not sure, just go ahead and rederive. So just check your work. What's little f of x? Oh, it's 5 times x to the fourth over 5. It's x to the fourth. Done. Okay, but is it the only one? And this process of checking should actually maybe be the hint. Because if I had just added a constant value here, say plus 2, then this derivative of f2 here would still be 5x to the fourth over 5 since the constant would be canceled. So this is a really important fact. We can have many antiderivatives. In fact, we can have infinitely many antiderivatives because what do we see? It doesn't matter what the constant is that you add on, it will still be an antiderivative. So, fact, any two antiderivatives of a function can only differ by a constant. So proof, let f and g be antiderivatives of lowercase f. Then cap f prime is equal to f. And cap g prime is equal to f. But that means that the derivatives are both equal. So cap f prime minus cap g prime is 0. And therefore, by corollary to the mean value theorem that we already proved in our mean value theorem video, cap f minus g is equal to a constant. So in conclusion, cap f equals cap g plus c. So the only difference between any two antiderivatives is a constant. Any two antiderivatives for the same function at least. So, the way we write this in general, if cap f is an antiderivative of f on an interval I, then the most general antiderivative of little f on I is cap f plus c, where c is any constant. Alright, so with that being said, we're going to just go through and look at a bunch of functions and find their antiderivatives. So I've disguised this as an exercise, but really every antiderivative that you are doing here on this is one that you're going to need to have memorized in the same way that you memorize your derivative rules. But these are just the opposites of those derivative rules. So if you remember your derivative rules really well, then all these are going to be is just a restatement of those things. So, sometimes we have to write it a little bit different. It's a little tricky when you're going backwards, but it's pretty straightforward. So here I have little f of x equals x to the n. So we're going to write the most general antiderivatives for each of these. So cap f of x, so we increase the power by 1 and divide by the new power, right? So that's exactly the opposite process of taking the derivative. So for the derivative of the power rule, you multiply by the old power and subtract 1 from the power. Here, you do it in reverse. You add 1 and divide by the new power. So that should be exactly what you'd expect. Now you can always check this by taking the derivative. If I take the derivative, I get n plus 1 times x to the n over n plus 1. Those cancel, and you just get x to the n back. Okay, so for b, well, this is 1 over x. So what function has the derivative 1 over x? Well, we know that the natural log has the derivative 1 over x, but we actually also showed that the natural log of the absolute value of x has this derivative. So from our previous example, from one of our previous lecture videos, we know that the natural log of the absolute value of x has the derivative 1 over x. So we can express the antiderivative of 1 over x as ln of the absolute value of x plus c. All right, well, we've got f of x equals e to the x here. So we know that the derivative of e to the x is e to the x, and it works the other way as well, of course. Cap f of x equals e to the x plus c. If you take this derivative, you just get e to the x, which is exactly what we want. All right, for d, f of x equals cosine of x. Now, that should be not too difficult. What function has the derivative cosine of x? Well, sine of x. And don't forget the plus c. Okay, now this one is slightly trickier. F of x equals sine of x. So what function has the derivative sine of x? Well, the derivative of cosine is negative sine, so that doesn't work. But if I have a negative in front already, so if we make this f of x equal to negative cosine of x plus c, well, the derivative of negative cosine of x is negative negative sine, which gives us positive sine. So that's, again, exactly what we want. All right, so for part f here, what function has the derivative secant squared of x? Oh, that's just tangent of x. Okay, what function has the derivative secant of x times tangent of x? Well, that's just secant of x. Plus c. All right, which function has the derivative 1 over 1 plus x squared? That's tangent inverse of x. And finally, what function has the derivative 1 over the square root of 1 minus x squared? That's sine inverse of x. So you're going to use these antiderivatives a whole lot. You definitely want to make sure these are memorized where you can pop these out really quickly. But again, if you know your derivative rules really well, there really shouldn't be much to it. You're just reversing that process. So that being said, let's go ahead and tackle some example problems applying these antiderivative identities. First, find a general antiderivative for f of x equal to 7 minus 4 times 1 plus x squared to the negative first power. So the trick with all of these problems is just going to be, you've got to get it into a standard form that looks like one of our regular antiderivative forms. Or maybe if I haven't written one here, you get it into one that will be obvious. So in this particular example, we'll see that there's an obvious one that I left off the previous list, but it should make sense once we tackle it. So first, I'm just going to rewrite this function as 7 minus 4 times 1 over 1 plus x squared. So now when we go to do the antiderivative, it should be a little more straightforward. First, we got to deal with the 7. So, I have a constant. What could have given me a constant for the derivative? Oh, well, just the same constant times x, right? Whenever we take the derivative of a constant times x, we just get the constant back. So my antiderivative should be the constant times x. Minus the constant 4 here times, well, the antiderivative of 1 over 1 plus x squared is tangent inverse of x. plus c. Okay, well that's it for that one. Let's move on. Find a general antiderivative for g of x equal to 3 plus t to the 1/2 power plus t squared over the square root of t. So for these, I need to split these up so that I can look at each one individually and rewrite them in a form where I'll know how to do something with it. First thing I'm going to do is rewrite my denominators, t to the 1/2. And then I'm going to write everything in the numerator. So 3t to the negative 1 over 2 plus 1, t to the 1/2 over t to the 1/2 plus t to the 2 over t to the 1/2. That's t to the 3/2. Just subtract our exponents there. So now, wow, I listed that as g of x. That should say g of t. G of t. So cap g of t. All right, well, let's take a look. We've got 3 times, so we increase our power by 1. This becomes t to the 1/2. So, you know, I can maybe write that step out really carefully. Negative 1/2 plus 1 divided by the new power. Negative 1/2 plus 1. Plus, we've got 1. Well, the antiderivative is just x. The derivative of x is 1. The antiderivative of 1 is x. 1 is t. Again, our variable is t here. All right, next. So we've got t to the 3/2. So we're going to add 1 to our power. Divide by the new power. Plus c. And we should definitely do a little bit of cleanup here. So this is going to be 3 times t to the 1/2 power. That's the square root of t. Divided by negative 1/2 plus 1. That's positive 1/2. Plus t. Plus t to the 5/2 divided by 5/2 plus c. And finally, this multiplying by the reciprocal instead of having fractions in the denominator, we get 2 times 3 is 6 root t plus t plus 2t to the 5/2 divided by 5 plus c. Okay, so next, find f of x given that f double prime of x equals 10x to the 4th plus 3, where f of 1 equals 1 and f prime of 1 equals 7. So we call this type of problem an initial value problem. So we're finding antiderivatives, but in finding it to fill in the blank information, because what do we notice with each of these general antiderivatives? We have some unknown constant. Well, we can get rid of those unknown constants if we know the conditions for the functions we're talking about. So that's what we're doing here. So since we have the f double prime of x equals 10x to the 4th plus 3, then f prime of x should be equal to 10 times x to the 5th over 5 plus 3 times x plus a constant. Now this constant here is usually going to take on a very specific value. I say usually, but as long as it's a polynomial, if we're dealing with polynomials, we're definitely going to see that this c is going to take on, well, we're going to see that this c is going to take on a specific value. So which value is that? Well, that's f prime of 0, because when I plug in 0 here, what do I get? I get 0, and all that's left is c. So this is not strictly true for all types of functions, but if all of your functions are going to be functions just multiplied by some power of x, then of course c is going to be equal to f prime of 0. But we don't know f prime of 0 in this case, so we can't really use that. But we can use f prime of 1, which is equal to 7. So we can plug that in, and just solve. So let me first simplify this a little bit further. 10 over 5 is 2. So this is 2x to the 5th plus 3x plus c. Okay, so f prime of 1 is 7. So f prime of 1 is also 2 times 1 plus 3 times 1 plus c. And this whole thing should be equal to 7. So this is 2 plus 3 is 5 plus c equals 7. So that implies that c equals 2. So if c equals 2, then we can just say that f prime of x is actually 2x to the 5th plus 3x plus 2. Okay, so now let's find our original function, our parent function, we could say, f of x. So we take the antiderivative, we get 2x to the 6th over 6 plus 3x squared over 2 plus 2x plus a new constant, we'll call it c2. Let's simplify f of x a little bit here. So we get f of x equals x to the 6th over 3 plus 3x squared over 2 plus 2x plus c2. And then we're going to just do the same process before. We're going to take this information, f of 1 equals 1, and apply it to the function we have here. So f of 1 is 1/3 plus 3/2 plus 2 plus c2, and we're going to set that equal to 1. All right, so what do we get here? Well, 1/3 is 2/6, and 3/2 is 9/6. 2/6 plus 9/6, that's 11 over 6 plus 2, which is 12 over 6, plus c2 equals 1, which is 6 over 6. So I subtract those, I get 23 over 6, I subtract it, I get c2 equals negative 17 over 6. So that leads me to my final conclusion for my function. F of x is equal to x to the 6th over 3 plus 3x squared over 2 plus 2x minus 17 over 6. All right, that's it for that one. All right, now we've got a couple examples here. So example 6, a stone was dropped off a cliff and hit the ground with a speed of 80 feet per second. What is the height of the cliff? So when we deal with these real-world problems, we have to think of everything in terms of a base reference here. What I mean to say is I can decide whether the top of the cliff is height 0 and the bottom is height 80, or if I want the bottom to be 0 and the top 80, or really any values I want as long as they stay 80 feet apart. Or actually, I should not say 80 feet apart. I should say whatever height it is. But I can set the top of the cliff as 0, or I can set it as my final height of the cliff. And you should generally do what's going to be most convenient for the problem at hand. So in this case, I'm going to draw my little picture of this cliff here. I'm going to set this as height 0. And then this will be our final height, right? So you've got an object dropping. And you want to know how tall that cliff was based on how fast it was going when it hit the ground. Okay, so what do we need? We have acceleration. We have the initial, the final speed. Well, we need to find the antiderivatives. So the acceleration is 32 feet per second squared. Well, what is velocity? It's the antiderivative of acceleration. So that's going to be 32t plus some constant. Okay, so what do I know about that constant? I know that that constant should be able to be solved relating to whatever information I have about the velocity. And I know that the velocity at the final time is 80 feet per second. Okay, so, well, what was the initial velocity? I'm getting a little bit ahead of myself. Well, the initial velocity is the moment the stone was dropped off the cliff. But if you're holding a stone in your hand and you drop it, the second you let go, the stone isn't moving yet at that instant, right? So the initial velocity is 0. So obviously it would be very hard to get my information about my velocity from this final time when it hits the ground. But can we figure out this constant from v of 0? Well, sure. V of 0 should be 0 plus c1, and that should be equal to 0. So c1 equals 0. So that's actually pretty nice. We get that the velocity is just 32t. Okay, now I want my position function. But position is, of course, the antiderivative for velocity. So I get 32t squared over 2. Again, I add 1 to my power, and I divide by the new power. Plus, I get a new constant. We'll call it constant 2. And what's this constant going to be related to? Well, it's going to be related to my position. But remember, we set the initial position to be 0 to make our lives a little bit easier. And this is where that pays off. So when I plug in 0 here, I guess I should label my position function height for consistency with my drawing. Okay, so height of t is 32t squared over 2 plus c2. So if the height of 0 is 0, then when you plug in 0, you get c2 equals 0. So my height function is just 32 over 2t squared, or 16t squared. Okay, so now the question becomes, based on what we know, how high is this thing? Well, in order to figure that out, I need to know what is the value for the final time here. All right, so we've got my height function. So we're going to do a little bit of work off to the side to figure out what TF is. So we know the velocity when it hits the ground should be 80 feet per second. So the velocity at time final should be 80, but that's got to be equal to 32t. So that means 80 divided by 32 equals t. That should be t sub f, t final. And so let's simplify this a little bit. So 80 over 32, that's going to be 5 halves. Yeah. So the final time is 5 halves, or 2 1/2. So then my height at the final time is really the height at 2 1/2 seconds, or 5 halves, which is 16 times 5 halves squared. That's 16 times 25 over 4. 16 divided by 4 is 4. 4 times 25 is 100. So this cliff should be 100 feet tall. Okay, so we're all done with that one, and now we got one more example to go through. Now this next one's a little bit of a tougher problem, but you know, again, I always like to make sure I show what the harder situations you can come upon look like. Okay, so for this last example, we have a car traveling at 60 kilometers per hour when the driver sees an accident 75 meters ahead and slams on the brakes. What constant deceleration is required to stop the car in time and avoid a pileup? So let's go ahead and just collect the information we have, what we know, what we want to know. All right, so what do we know? We know the initial velocity when the driver slams on the brakes is 60 kilometers per hour. We can set the initial position of the car to be 0, right? And we can choose what we want to label the initial position. And we also know that we are looking for the acceleration constant, k, and we want the position at the final time to be less than 0.075 kilometers, which is, of course, 75 meters, but we need everything to be consistent in terms of units. Okay, so what does this tell us? Well, this tells us that the initial velocity, the velocity function is the antiderivative of acceleration, which is the constant k. So we get k times t plus a constant c, called c1 here. And since v of 0 is 60, we get 0 plus c1 equals 60. So c1 equals 60, and hence the velocity at any time t can be given by kt plus 60. Okay, so what else do we know? Well, we know that the position function is the antiderivative for velocity. So this is going to give us k times t squared over 2. Increase the power by 1, divide by the new power, plus 60 times t. The antiderivative constant is just the constant times the variable, plus a new constant c2. But p of 0 equals 0. So we get 0 plus c2 equals 0. So of course that implies c2 equals 0. So p of t is just k t squared over 2 plus 60t. So now we need to figure out an expression for our final time in order to plug it into our position function to check when it will be when we will stop in less than this distance. So how do we find an expression for our final time, the time when the vehicle has stopped? Well, the vehicle stops when the velocity is 0, right? That's what we want. We want the vehicle to stop, so the velocity will be 0. So that means we want k times the final time plus 60 to be equal to 0. Subtract 60. Divide by k. That gives us t sub f equals negative 60 over k. So this implies that our position at our final time should be k over 2 times negative 60 over k squared plus 60 times negative 60 over k. Negative 60 squared is 3,600. So we get k times 3,600 over 2 times k squared. minus 3600 over k. K over k squared is 1 over k. 3600 over 2 is 1800. And 1800 over k minus 3600 over k is negative 1800 over k. But remember, what did we want? We wanted this position at our final time to be less than 0.075 kilometers. So we want this to be less than 0.075. And so if we just solve this inequality, we multiply k across, divide by that, we get negative 1800 divided by 0.075 should be less than k. So in other words, k needs to be greater than approximately. All right, let's plug this into my calculator here. Negative 24,000. And this is going to be in kilometers per hour squared. And I'm just going to make sure I didn't miss any constants here. 3600 squared. Okay, that's 1800. That's minus. Okay. Okay, so that looks good. All right. So k is greater than negative 24,000 kilometers per hour squared. Now that seems like a really extreme number for acceleration, but keep in mind, most of our acceleration numbers are measured in much smaller scales. If we converted this to meters per second squared, it wouldn't seem quite as extreme. All right, well, that's it for this one. Thank you for watching.